Go ahead.
Yeah, so I had a question on 11 and 13 from 2.3.
11 and 13. For people who have this, who raise your hand and have the same question, you can lower your hand now because I'm going to go over them. And your question will be exactly the same except for the numbers. So the answer won't work for you, but the procedure will work definitely for you. Okay, so let's go over 11 and 13. Nick, oh, good, good, good. 11. Limit. H goes to 0. 4 over 3x plus h square minus 4 over 3x square divided by h. Okay. Like I said, principle, plug in a number. Hopefully it works. If it worked, we are done. Plug in a number, you can easily see the two terms become the same. You minus them, they become 0 on the top. Similarly, the 0 on the bottom. So you have 0 over 0 case. Now we have done this enough of time. You need to be able to differentiate between two cases. The first one is 0 over 0. The second one is 3 over 0, or some number over 0. Okay. Now, if you think about it, 3 over 0 is really like something like 3 over 0.00001. This one is going to give you positive or negative infinity, depending you are approaching 0 from the left or right. So a fixed number divided by 0, it's basically the vertical asymptote. You check the left and right and see if they are the same infinity. Okay. Now 0 over 0 is different. That's almost like the top is small and the bottom is also small. From here you can see it really doesn't give you any clear answer for what the number is, because for this case it's 1, but this one can also be that case, then the answer is 2. So it really depends on how fast do you go to 0. Therefore, for 0 over 0 case, it's not vertical asymptote. It's something else, which is a hole. That's how I think about it. Okay? Both cases are dividing by 0, but 0 over 0 is the one with the hole. For that case, our job is try to cancel the hole, hopefully. And you can think about another thing. When h goes to 0, you produce 0 on the top and 0 on the bottom. That probably means h is going to be a factor. Eventually, you cross out. When h goes to 3, you have 0 over 0. That means h minus 3 is probably the term you're going to cancel out because that's the factors for the zeros. Therefore, my job is going to try to look for h on the top, look for the h on the bottom, and hopefully they cancel. Then the 0 problem is gone. That's the idea. All right. Now let's think about how to do this. We noticed there's no conjugate. This is a big fraction. I'm going to do this minus this. Times 3x squared. So far, that's everything in the red box. And when I finish, I want to divide by h, okay, which looks not pretty. So let's change it to be times 1 over h, which is the same. The rest, we want to produce a h on the top, which means we have to cancel terms. We need to FOIL everything out. That's how we FOIL a perfect square out. Keep the bottom, okay, times 1 over h. Be patient. It's a lot of terms. Okay. 4 times 9 is 36x squared. 2 times 3 is 6 minus 24xh plus, which is minus 4h squared. Coming from this term here. when you distribute the negative inside, make sure you flip everything. Okay, and they cancel. Now notice the top clearly has a common factor h, which is exactly what we're trying to cancel out. Okay, and eventually this will be gone. Okay. So finally, let's plug in h equal to 0. That's basically the answer. Okay, now simplify more to make it pretty. Divide x on both sides. We have x to the cube on the bottom. The x is gone. We have a 3, we have an 8 and 27. So that will be the simplest answer in the end. Let's try that. -8 divided by 27, x to the cube. That's the answer. Yeah, it worked. Okay, so the key, realize it's 0 over 0. You need to rely on algebra, and then probably for this case, you just need to do the common denominator, cancel everything you can cancel out by FOIL everything out. Luckily, it worked. Cool. Any question before we move on to 13? All right, let's check 13. Oh, that's a good question. Okay. Limit x goes to 2 minus 2x plus 4, absolute value x cubed plus 2x squared. 2 minus, it's 2. So 2 times 2 plus 4. Can't be 2. Okay, -2. My bad. -2 minus. -2 minus. So 2 times -2 plus 4, the top is 0. The bottom, you can see it's -8 plus 2 times 4, which is also 0. So 0 over 0 case, we're going to cancel something out. Now, what should we cancel out? Well, we realize the top is this if you factor things out. The bottom is this. All right. So clearly, we should cancel these two out. If the absolute value is not there, stopping us. Good so far? So our job is try to remove the absolute value bar. Okay. Well, how do you remove the absolute value bar? It's actually pretty easy because you only have two choices. Okay, what should I put on the bottom? It's either this one or the negative of this one, because that's what absolute value means, right? It's either this or that. Which one to take really depends on which one is positive, because absolute value will only give you something positive. All right. Now, we're trying to decide what's the sign of this, positive or negative. What we know is x goes to -2 minus. Here is how we do the argument. Question 1, is x bigger or less than -2? If x goes to -2 minus, think about it, that means here is -2 and x is on the left. X is less than -2 based on this fact. If that's the case, what about x plus 2, which is nothing but moving this one to the other side? It should be less than 0 then, right? What about this one? Remember, we're looking for this one. Times x squared. It should be less than 0 times x squared. We know it depends on what we times, right? We times something positive, then the sign remain negative, less than. If we times something negative, we need to switch the sign, okay? But we happen to be timing x squared. Therefore, it's still less than. So if this is less than 0, what about the absolute value of this? Can you see we should start to pick this one and cross out this one because that is negative? That's the whole argument I am going to do for the absolute value here. It's a lot of work, okay? But this is how I think about it. Then let's block out this. These are side notes. Then what I really should do is going from here to here, or let's say going from here to here, I'm ready to remove the bar by putting a negative sign in the front, because I know the thing inside is negative. After that, there's no bar. Let's cancel. Which is 2 over negative 2 squared, which is 2 over -4, which is -1/2. Okay. So the key is from here to here to remove the bar by analyzing, am I dealing with something negative or positive? Using the information here. This works for any question involving absolute value because you basically just remove the absolute value. And the way to remove it is to know the thing inside is positive or negative. Sounds good? Okay. Aaron, do you still have questions or it's one of these two? Okay.
No, it was one of them.
Okay. And Kenyon? One of them, or do you have more?
No, that's it.
That's it. Okay. Cool. They are good questions. I'm very likely to put those kind of things in the exam. They're not impossible, but they are not just trivial, right? Okay. Very good. All right, so let's move on. Let's move on to 2.5. We want to talk about continuity. Why do we want to talk about continuity? Now keep in mind, the thing we're trying to do here is try to find the changing rate, which is the derivative. Right? We're doing all the preparation just for that. But here's the thing. Before you go ahead and try to find something, right? I ask you to find a unicorn. Are you going to just go ahead and do it? No, you say, I need to make sure that unicorn exists first. Okay, and you want to make sure there is one. So before you actually go ahead and try to find the derivative, you need to make sure the function is differentiable, which means it does have derivative, so I can go and find it. Okay. And now in order for a function to be differentiable, to have a changing rate, that thing has to be continuous first. Even continuous is not enough, but if it's not continuous, it's definitely not differentiable. Make sense here? Okay, so this is the preparation work. If I go ahead and say, hey, please find the derivative of fx, you need to say, hey, I want to make sure it's differentiable first. But then I realize, okay, I want to make sure it's continuous first. If it's not continuous, don't even bother. There won't be a changing rate. Okay, so that's the reason we're going over this. Cool. But don't we already know how to do it? Like, what do you mean by continuous? Well, this is continuous. Okay, what is not continuous? Well, this is not continuous. This is not continuous. This is not continuous. Right? We already know this. What do? You draw the graph. You draw the graph and make sure that you can draw it continuously, smoothly. Or you can say, without your pen leaving the board. If you have to draw this, you have to leave the board somehow and jump back again. Then your thing is not continuous. Otherwise, you won't have to leave the board. Still okay? Which is fine. This works before. But now we want to have a better definition simply because now things get tricky. For example, is this one continuous? Let's say at x equal to 0. I'm not going to switch the screen, but just recall that's the thing we draw in class with a computer. It looks like this, yeah, whatever. But then, like that. Okay, and no matter how we zoom in, we find it's really impossible for me to tell if there is a hole because it seems like there is no hole. No matter how you zoom in, it's all fixed. If there a jump, well, they're all fixed. They're all mixed, right? And is there a vertical asymptote? It seems like there is no vertical asymptote. So just by looking at the graph, it's really hard to tell is it continuous or not because we could never zoom in enough. So hard to tell. Do you see the limitation of just knowing this? Because it cannot handle what we have here. Okay. Another example, which is even more straightforward. There is some function called the Dirichlet. Am I spelling it right? Yes. Okay. Well, I'm not a native speaker, so if I spell it wrong, just bear with me. Google something. If there's one letter off, yeah, trust the web. Dirichlet function. It's a function defined on 0, 1. And this is the formula. It has two values, 1 or 0. If x is in 0, 1 and x is rational. Similarly, this will be the rest, which is irrational. We have never seen anything like this before, but it's simple. Let's try to get a feeling of it. What is f0? Is 0 rational? A rational number? Then the answer is 1. It is rational. What is f1/2? Is 1/2 rational? Yes, then the answer is 1. f2/3, any fractions is going to be 1 because you're rational. Sounds good? What about f square root of 2 over 2? Well, square root of 2 over 2 is irrational. Therefore, if you put an irrational number in, you should produce 0. You put a pi over 4 in, you should have 0. Any irrational number you put in, it's going to be 0. Still okay? From here, you can see this is clearly a function because if you put one number in, you either get 1 or 0, but you don't get both. You don't get confused. Okay? So this one passed the vertical line test. It's a function. How do you draw it? f0 is 1, so clearly it passed this point. 0, 1. It passed 1, 1. It passed 1/2, 1. It pass 1/3 one. It pass, as long as you put rational number here, you are going to have all the points here. Good so far? Meanwhile, for the ones which are irrational, for example, square root of 2 over 2, it's 0.7 something. So roughly, it should have 0. For irrational numbers, it should have zeros everywhere on this line. Good so far? I draw probably, I don't know, 10 points. But how many points are there you should draw? How many rational numbers are there between 0 and 1? A lot, right? How many irrational numbers are there between 0 and 1? A lot. So what you should really draw is, you should draw all the possible ones, which will give you something like that. Meanwhile, it gives you something like that. That's the graph of the function, if I have to draw it. Make sense here? Looks like this one is continuous. But you know, there are gaps in this line, right? Because this is a irrational number, and the next rational number, there is definitely some irrational number within. So somewhere from here to here, you dropped here, and then you come back again. Make sense so far? The problem is, how big is the gap? Small, really small. Because any two close rational number, there's always an irrational number within. So the gap is actually so small that you cannot tell, no matter how much you zoom in. Make sense here? No matter how much you zoom in, it's always dense if you just tell by your eyes. But you know there are infinite many gaps inside. You just can't see it. Make sense to everybody? Again, how can I tell if this one is continuous or not? And from our experience, this one should be not continuous. Of course, you have a lot of gaps, but by looking, I can't tell. I don't see a hole. I don't see a jump. At least some jump I can see by my eyes. There are actually jumps, right? Infinite many jumps. So again, restrictions, hard to tell. And we have many more examples if you want to see. But I think I convinced you that this is great in the sense that when things are simple. Okay. When things get complicated, this is not enough. Sounds good? Okay. When does things fail? This case or this case. Either way, things get messy when you deal with infinity, when you deal with something extremely small. But we do have a tool to handle things which are extremely small. That is called the limit. Therefore, if you have those kind of tricky case, where you have something super, super dense, everything is so small, so close to 0, let's redefine continuity. But this time, let's define it by limit. And the idea is quite simple. A function fx is continuous at a point if this is satisfied. Is it continuous or not? You just check. Does the limit equal to the function value? And you know how to find the limit, right? Okay, then you can check. Sounds good? Okay. Well, is this one continuous? Now the answer becomes, let's just check this. And let's check this. Okay. And let's check if they are the same. If they are, continuous. If they're not, not continuous. Period. Sounds good? What's the limit? Does not exist. Remember oscillation? Yeah, there's no limit. Does not exist. What's the function value if you plug 0? Does not exist. That means what? That means you cannot even compare them. Because there's no such thing called this. And there is no such thing called this, not to mention they are equal or not. No, no, no. We can't compare. Therefore, this one fail, right? Therefore, not continuous. The reason is because you don't have a limit, you don't have a function value, so there's nowhere even to mention are they the same. Make sense so far? So here's the good thing. Number one, we don't have to draw the graph. We just need to find the limit, which is great, which is basically web work from 2.3 and 2.4. Okay, that's finding the limit. We know how to do it. Okay. Second, for something which is confusing, when you draw it, you don't know if there's a hole or something by looking. Now you have something really reliable. Just compute. Okay. Are we good on this? So from now on, if I ask you, is a function continuous at 5? What do? You plug in 5 to find f5. That's one number. You also find the limit at 5. That's another number. What can happen? What can happen is, number one, this one maybe does not exist. Then there's no way to compare. Automatically, no limit. Sorry, not continuous. Okay. What else can happen? This one does not exist. Then, of course, not continuous. What else can happen? They both exist, but they are not the same as each other. Then again, not continuous. Still okay? So finally, if both exist and they're the same, that's the moment you're going to say it is continuous. Okay? That's the logic. Of course, we should connect this with everything we had before, like this, like that. Like, how do you understand the old thing in the new way? Let's actually talk about the discontinuities. When this one fail, how does this formula capture what we had before? Discontinuous cases. Okay. The first one, what if we have something like this? Or maybe something like this. Okay, we know it's not continuous, right? Therefore, we know it fails this formula. Okay, how does it fail? Well, for this case, you can see, you can compute limit x goes to a fx, which should be here at the circle. But there's no fa, because fa is not defined. So of course it failed. One side is missing. Good so far? What about the second case? Well, you do have a limit. You also have a fa. This time it's not missing, it's here. Okay, but the limit is here, and fa is here. Are they the same? No, therefore not continuous. Good so far? From here you can see this is the first type of discontinuity. We call it removable, because other than the hole, you are basically continuous. So removable discontinuity. Okay. Now the second case. We have a jump discontinuity. What happened this time? Well, fa is here. Limit x goes to a, fa, fx. What's the limit at here? Does not exist. Therefore, fail. You cannot compare fa and the limit, because limit, your left side is missing. Therefore, not continuous. Good so far? And the reason is because the left limit is not the same as the right limit. Therefore, no limit. You have a jump. Of course, then not continuous. Number 3. We know it's not continuous, of course, right? We call it vertical asymptote. What happened to this case? What's the limit? Does not exist. Then don't compare. Of course, it failed, not continuous. What happened to this case? This time, the limit is there. The limit is infinity. What about fa? If you have an infinity here, what's the function value at this point? Nothing.
Yeah, sorry.
Brittany, I may ask you to mute yourself. Awesome. Okay, yeah, thanks. Okay, let's say it again. Can everybody see that? The limit exists, it's infinity, but there's no way to compare because you don't have a function value here. So either way, not continuous. Finally, you have a case. Sine 1 over x. And for this case, we just did it. The limit does not exist, which is already good enough, but also fa does not exist. So either way, not continuous. We give it a name. We call it oscillation. Okay. Does everything make sense to everybody? Everything we had learned before is included in that one little tiny formula. Plus, we have a lot of new things which can also be handled with the tiny little formula. And this formula is not afraid of something super small. Something goes to infinity because limit is just invented for that purpose. So not we're all equipped. I may ask you some questions like this in the exam. Such as, can you identify where the discontinuity is? Let's say discontinuities are. And also what type of discontinuities. I know it's super easy, but you should also know the terminologies when you talk with other people. By saying a hole, don't say a hole, we call it removable. And see a jump is jump, okay? And also vertical asymptote compared to infinity. So just be more professional. But I think you get the idea. It's just the terminologies. That's something I may ask in the exam. All right. Any question before we move on? Awesome. So we defined continuity, a single formula, and all kinds of fancy ways that formula can fail, which is discontinuities. The third thing we want to talk about is called one-sided continuity. Which is basically left continuous and the right continuous, instead of saying continuous in general. The idea is quite simple. This is left continuous. That means if you just look from the left, it's continuous. And then this is the right continuous. Exactly the opposite. This is dash, this is firm. So left continuous, right continuous. Is it continuous? It really depends on what this part look like. It may be here, then it's not continuous. Or maybe it's here, then it is continuous. Good so far? All right. Now I think it's easy to see. To check this, you just to check equals FA, but this time not from both sides, just from the left. Okay. And then we can say Fx is continuous. If it's both left and the right continuous. So when you say continuous in one dimension, you can basically say, when you say continuous, it means it continues from both sides. It means left and right continuous at the same time. But sometimes you may only have one side, not the other side. Sounds good? Okay. Why do we care about this kind of thing? Well, number one, this kind of thing is bad, you know? It's not as good as continuous. But it's not so bad because you can still talk about continuous from one side. For example, in this case, on the left, even though you have a jump. Good so far? Okay. What's the application though? Well, now you need to think about it. Continuous is trying to serve differentiable. Differentiable is trying to serve the changing rate or derivative. So if you're only left continuous, you should have something which has a left derivative or left changing rate. Makes sense here? And also you can have a right derivative. That means what? That means if I know everything, all the thing up to September, today is 16th. Okay. I want to know what's the changing rate here. Do you realize you can have two approaches? The first approach is check everything before September 16th, all the way up to September 15. Look at the historical data, and then you can see, oh, I'm going to guess 16 is going to be like this. Good so far? Meanwhile, there is another way you can do it. You can check everything backwards all the way up to September 17th. You can have a second guess, which is using all the data after that day. The first one is everything before that day. Good so far? Okay. And can you see that? These two may not agree with each other. No, let me close the window. Okay. Yep. Does it make sense here? So this is almost like a left changing rate. This is almost like a right changing rate. Okay. So you have two different rates. So if they agree on each other, everything here is easy. Before, after, they are the same changing rate. That's fine. But in real life, something also can happen. That is, before this one, you're changing really slow. But after this one, you change really fast. And this we call the transition point. That is when the behavior dramatically changes in terms of changing rate. Okay, that can happen. For example, if you have a nuclear bomb, you have a certain threshold. Aaron, I'm asking you to mute your mic. Yeah, thanks. Okay. Now think about what's going to happen. Before you hit the threshold, everything is pretty slow. Okay, that means you have a slow changing rate. That means you have a slow left derivative. But after that, you're going to have something dramatic. That's what we call a bomb. Make sense so far? So just look at what happens before the threshold. There's no way you can guess that thing is going to explode. Okay, but if you backtrack everything, there's no way you can guess what happens before because this thing is so dramatic. That's the place where we want to use two derivatives, and they both have special meanings. Okay, sounds good? Okay, so left and right derivative corresponding to a transition, and then they corresponding to left and right differentiable, then they correspond to left and right continuous. So that's why we are doing this. And it's quite easy. All right. Now number 4. Now we want to talk about continuity on a interval. What do you mean by fx is continuous on an interval? AB. Then it means it is continuous. At every point in AB. Okay. For example, y equals x squared is continuous at x equal to 0 for sure, but also we can say it is continuous on 0, 2. That basically means it's continuous everywhere. You don't find any hole, any vertical asymptote anywhere inside. That also means later you can find derivative anywhere on this interval. Sounds good? Cool. What's wrong with it? Pay attention here. Number 1, why AB? Instead of AB with a bracket or maybe a half bracket. Why do you want something open, not closed? Well, if you think about it, this is A, this is B. Is this one continuous here? Of course, right? But if you look at the starting and ending point, do you realize that for this one, you can only talk about left continuous because there's nothing on the right? And for the beginning, you can only talk about the right continuous because there's nothing on the left. But if you want to say it's continuous, you need both. Therefore, we use open instead of closed because the ending points are hard to talk about. They only have one side. That's the reason. Sounds good? That also means is 1 over x continuous on 0 to infinity? Now, if you take a look, this is the interval. I'm not including 0, and the behavior at 0 is really bad. You have infinity. Make sense so far? But still, it's safe for you to say it's continuous here because it's just 1 point, and we don't include it. That means even if you have a vertical asymptote, but as long as that asymptote does not stop your interval and cut them into 2 intervals, okay? If it just happens on the right edge or left edge, it's fine. That's the point of ending points. We don't include them. Okay. Second, sometimes you will see a statement like this. Fx is continuous. Period. They don't give you a point. They don't give you an interval. Okay. Now you have done this multiple times before. Then you know there's a hidden condition. Basically, when you see this, they mean Fx is continuous on its domain. So sometimes if there's nothing here, they automatically means this. Okay. Now here the question. Is y equals 1 over x continuous? What do you think? Not really. Why? Not at 0. At there, you have something vertical asymptote. Sounds good? Okay. But now think again. What do I mean by this if I don't say anything? My hidden thing is y equals 1 over x continuous on its domain? That's what I really mean. And what is the domain of 1 over x? That is this. You said it's not continuous at 0, but does the domain, do I care about 0? I'm not asking about 0. I'm asking everything on the domain, not including 0. Therefore, this is where the edge is. Your answer for this question is yes. Should be yes. Even though clearly there is somewhere it's not continuous, but it's not in the domain. Okay, so this is the hidden question when they ask this. And because the hidden question includes this, which basically throw the 0 out, then that means you don't have to consider this case. The answer is yes. Okay. So if you want to differentiate it, it's basically the difference between ask is y equals 1 over x continuous everywhere? The answer is no, not at 0. Is y equals 1 over x continuous everywhere in its domain? The answer is yes, because 0 is not in the domain. Okay, try to see the difference. Sounds good? Okay, that's some careful terminologies. Here comes the third thing. That is interesting. How do you show this one is continuous? Well, it's easy. Just show this. Because this is the formula we did, right? Okay. So you show it's continuous everywhere in this domain. You just test every single point in the domain and say everybody satisfy this, then period. Do you see the problem here? You can check one point at a time. How many points are there in the domain? Infinitely many. How do you convince people this one works for any A? This one works for negative 99. This one works for negative 98. This one works for negative 97 or 98.03. Do you find that there's no way you can check all the points? And then you realize it's really easy to check it's not continuous at 0. Because you know where the thing failed, right? And it's just check, when x equals 0, use this formula, done. But when you want to check it works for every single thing in the domain, there's no way you can exhaust all the possibilities, right? Okay. Then how are you supposed to tell some function is continuous in a domain on infinite many numbers? Again, we go to mathematicians who has done this for you. So now you can actually use it without proving anything. That is, all simple functions are continuous on their domain. That means if I tell you y is equals tangent x, is it continuous? Then you just say, yes, it is continuous on its domain because it's a simple function. Why is that? Mathematician has proved that, period. Sounds good? That also means this one is continuous as long as you exclude the domain. So on everything, every point, at every point, except for x equals n pi, n equals 1. N equals positive, negative 1. Actually, 0. 0 should also be included. 0 plus minus 1. Okay, positive, negative 2, and so on. Other than these points, which is not in my domain, I am continuous. Sounds good? Okay, so for now, any simple function, go ahead and try to say it's continuous. Then later, go ahead and try to say nothing has a derivative. Okay? Again, what about this one? What do you think? Is it a simple function? No. It's 4 simple functions. This one, I know where it's continuous. This one, I know where it's continuous. This one I know, and this one I know. How do you combine them to be the one we want? F plus G, F minus G, F times G, F divided by G, and finally, for this case, F circle G, which is composition. Make sense so far? Okay, so this is, again, we're applying what we had before. Number one, we show it works for a simple function, which means polynomial, rational. You should, okay, follow my list. You should be able to produce that list now. We have 7, remember? Polynomial, rational, exponential, trig. That's 4. Okay. Trig has a trig inverse. Exponential has an exponential inverse, which is log. Polynomial has an inverse, which is square root, which is radical. That's the 7 things we know are continuous as long as they're in the domain. Sounds good? After that, we just need something to handle this. What should we call them? The law of continuity. Make sense here? Do you really need a law of continuity? How did you define continuity? I use limit. Then basically this one is guaranteed by the law of limit because continuity is nothing but a type of limit. And do you have the law of limit? Yes, we do. It's in 2.3. Good so far? Okay, so now everything is complete. From now on, you can use the law of continuity. Actually, there's nothing called this because it's basically just the law of limit. So it's not even worth a name for itself because you're just applying limit laws. Do you see the advantage of defining continuity in terms of limits? Then you can use the law of limit. Okay. What about derivative? Later we're going to define derivatives, remember? But we define derivative by limit. Still okay? Then we are going to have the derivative of all the simple functions and the law of derivatives. And then we realize we don't need it. The law of limit guarantees the law of derivatives because derivative is another limit. That's the power of generalization. Sounds good? All right. Next time, we're going to write down the details, like simple functions, what they are, and how you combine them. But basically, the answer is just, no matter how you combine them, as long as you're okay with your domain, you will be continuous. But let's save it for next time. Okay? Class is over. Feel free to leave, and I will stay for questions.